So the next speaker is Tuğba Hırlı. Now our mentor will introduce her to us.
Hello, everyone. It's a great pleasure to introduce Tuğba Hırlı. Tuğba is a rising third-year student at the Boğaziçi University in physics and mathematics. She will talk about an introduction to topologically ordered phases through a simple model, the toric code. This was a difficult subject, but Tuğba did an excellent job tackling it. And as you will see, Tuğba, the field is yours.
Thank you. So as Ege said, we have worked on the topological order and we use the basic model for this order, the torical. So in my presentation, I will firstly introduce what topological order is. Then we will continue with the toric code and show the properties for a system to be called topologically ordered using our model. So before defining topological order, I need to show why topological order is important for us. Until 80s, it was believed that Landau symmetry breaking theory could explain all the phases and phase transitions. And actually, it basically says that if two systems have same symmetry, but their ground states have different symmetry, then these two systems have to be in different phases. But in the 80s, with the discovery of fractional quantum Hall states, it was realized that Landau theory couldn't explain all the phases because it fails to explain these FQH states. So there's a figure here for the FQH states that shows us the phase transition with the increasing magnetic field. So here all the horizontal lines correspond to phase transitions. And in this FQH states, all phases in this figure have same symmetry, which Landau theory cannot explain. This means this FQH states have different order, which we call as topological order. So now we can define topological order. There are two properties for a system to be called topologically ordered. First of them is energy gap. And it is like in this figure, there has to be a finite gap between ground state and first excitation states. And the other property is that have quasi-particle excitations with non-trivial braiding statistics. Braiding statistics actually spin statistics with elementary particles, fermions, and bosons. But I will explain all of these better in the later of my presentation, so don't be afraid if you didn't understand it. So now we can continue with the toric code, but to be able to understand the examples and solutions that we are going to see, we need to learn some properties and axioms in quantum mechanics. So first things that they say is that in the space that we use is Hilbert space. And in quantum mechanics, we represent each physical state with a ray. Rays are actually vectors, but in quantum mechanics, any non-zero scalar multiplier does not change the state of the system. So what does it mean? If I choose a direction, then each vectors in that direction actually corresponds to the same ray, so corresponds to the same physical state. So I call these vectors cat and denote like here. And I said that each vector in cat space has a corresponding vector in its dual space, and I will call them as bra, and I will note them like this. So if I want to take the dual correspondence of a vector with the multiplier, I also need to take Hermitian of that multiplier, like the equation here. So the other terms that I need to explain is observables and measurements. I say that for observables are self-adjoint operators, and when I multiply that observables, I mean my operators with the state, I get the eigenvalue and eigenvector, which means that, which I say actually, the measurement of an observable prepares the eigenvalue of that operator. And after the measurement, the state we multiply becomes the eigenvector that corresponds to the eigenvalue that we get. So last things to say is the pole matrices. You may have seen this before, but sigma x and sigma z is especially important for us because all the operators that I'm going to use in this model consist of sigma z, sigma x, or sigma z. So let's look two of them in detail. In quantum mechanics, we represent each space with two-dimensional vectors. So actually, the eigenvectors of this sigma x and sigma z correspond to these spins. For instance, here, eigenvectors of sigma x are for this one, for instance, the first one is the spin up in the x direction, and the other eigenvector corresponds to spin down in the x direction. Same is valid for sigma z operators, and as you can see in this equation, the eigenvalue of both sigma x and sigma z either 1 or -1. So since I know all the things that I need, I can define the toric code now. Toric code is exactly solvable spin 1/2 model on the square lattice, and this lattice is embedded in a torus with genus 1. And as you can see in the figure in my toric code, the spins are located on the edge of the lattice. So the Hamiltonian of my system is given with this first equation here, and as you can see, there are two different operators in my Hamiltonian. The first one is AS, which I will call a star operator. It consists of sigma x matrices, and as you can see in the figure, it acts on each vertices of my lattice. And the other one is BP, which I will call as placket operator. It consists of sigma z matrices, and it acts on each different placket on my lattice. So from now on, to be able to solve the equations that I face, I need to understand computational relation of my operators to be able to solve them. So let's look at here. Even though sigma x and sigma z normally anti-commute, my star and placket operator will commute because, as you can see in the figure, these two operators have either 0 edge in common or 2 edge in common. For instance, here they have no edge in common, but if my placket operator would be in here, then they would have 2 edge in common, which results in 2 minus and so plus, which means that they will commute with each other. So since I know how my operators works in the Hamiltonian, I can calculate the energy of my system in the ground state. So here Hamiltonian is my observable. So when I multiply it with my state, the eigenvalue that I get from this equation will be my energy. So I know that ground state is the minimum energy level. So this means that from this Hamiltonian equation, I need to get the minimum value. And to do this, due to minus here, I need to get maximum term with this AS and VP term, right? So what I also know is that sigma x and sigma z can get minus or plus 1 as an eigenvalue. So in this case, to get the maximum term with these operators, I need to get plus 1 as an eigenvalue in the both of them. But there is a question that we need to ask ourselves. How can we be sure that these two operators can get an 1 as an eigenvalue at the same time? To answer this question, a theorem can help us, and it says that if two Hermitian operators commute, then there exists at least one basis of common eigenvectors that diagonalize them both. So in other words, it says that since my star and placket operator commute with each other, then I can diagonalize both of them simultaneously. So now I can write these two equations with constraint that I need to get 1 as an eigenvalue. And using these equations, when I explicitly write my Hamiltonian, after the multiplication with these ground states, I'll get 1 from here. So only thing left will be number of stars and number of plackets. So the last equation, the last parenthesis here corresponds to my ground state energy. So since I have found the ground state energy, now I can take a look on the excitations on my model. And there are two excitations. One of them electric path operator and the other one is loop path operator. So let's first look at the electric path operator. It consists of sigma z matrices, and the first figure here that you see shows how this electric path operator acts. So since both electric path operator and my placket operator in the Hamiltonian consist of sigma z, I said that they can commute with each other. So let's look at what happens with star operator. So if I apply my star operator in these vertices here, since they have 2 edges in common, they commute. But if I apply my star operator in the boundary points, since there will be only one edge in common, this means that they have to anti-commute. So only effects that of my operator will be on the boundary points of this path, right? So this means actually the path I choose does not matter. So for instance, here, instead of this operator, if I choose this path, if I choose the path above this, then it wouldn't matter because the only effects comes from the boundary points, which causes that we say that it creates two particles in the boundary points, which I will call for electric pet operator E particle. So same thing is valid for dual pet operator. It consists of sigma x matrices, so it will commute with my star operator, but it will not commute at the boundary points with the placket operator. And again, it will be like it creates two particles at the boundary points, which we will call as M particle. So these equations show the anti-commutation relation that I just said. Since we know how these excitation operators behaves, now I can find the energy difference after the excitations, and let's here do it for the electric charge excitations. I know that electric pet operator only commutes at the boundary points of the star operator, so it's enough for me to focus on these 2 points. And after the calculation, I found that I have 4 JE difference from the ground states. So if I had done the same calculation for the magnetic pet operator, then the energy difference would be 4 JM. So this means that according to which one is smaller, the gap between the ground state and the first excitation state will be 4 JE or 4 JM. So this actually shows us the energy gap, which was the first properties for a system to be called topologically ordered systems. So now we need to show the second property, which was the braiding statistics, non-trivial braiding statistics. But to be able to understand that, we first need to. So in quantum mechanics, we said that identical particles are distinguishable, and this means that if I change places of 2 identical particles, then my state does not change. But at first, I said that if I multiply my state with a non-zero scalar, then it will still correspond to the same state. So when I change the place of 2 identical particles, a non-zero multiplier, let's call it C, can appear. I will call this multiplier as phase factor. And since in quantum mechanics we normalize the states, the C can be represented with e to the I phi. And in 3 dimensions, we know that this multiplier can have a value plus or minus 1. If it's plus 1, we call that particle boson. And if it is minus 1, we call that particle fermion. So let's now look at the 2 particles that we have created in the excitations, E and M particle together. So assume I have changed place of 2 E particle. What does this mean? I change the place of the operators that create E particle. But since the operators creates these E particle commute with themselves, this means I will get still 1 as a phase factor, which corresponds that these particles behave like bosons. So since we know everything that we need in 3 dimensions, let's look at the 2 dimensions since our model is in 2 dimensions. So here, this multiplier C can take a value other than plus or minus 1. And we call these particles that behave different than the 3 dimensions as anyon. Trivial braiding statistics in the toric code. So here, I first create 2 EM particles into different points, as you can see. So I will solve this question with 2 cases. And in this one, in the first case, I will move my first particle to the point 1 and second particle to the point 2. And when I denote this operator that moves my E and M particle, so for instance, let's call case for that moves E particle and gammas for the movement of M particles. So when I write the operators in order, I'll get my new state. So here, let's look at the anti-commutation relation. And as you can see, there is only one edge that 2 different operators intersect. So I can say that these 2 operations will anti-commute. So since we understand the first case, now let's look at the second case. In here, the difference in here is that this time I will move my first particle not to point 1, but to the point 2 this time, and the second particle to the point 1. So again, when I denote my operators with K's and gammas, then I will look at the intersection. It's still on this edge. So when I write the operators here, I can see that they will anticommute. So at the end of the two cases, I know that I have two identical EM particles in these 2 points, right? In both of them. Sorry. So I can say that it is like I have two EM particles, then I change the place of them, right? So to be able to calculate the phase factor that appears, I need to calculate this equation here. So in addition to anticommutation relation that I know, I need one more information to be able to solve this equation. So as you can see, the K operators that moves E particles, if I multiply them, they act on this blue path. And it is the same path with the first cases, as you can see. So this means that if I multiply all the K's together, I will get identity because it will be like on the same edge, I get sigma z squared, which corresponds to identity. And same thing is valid for the operators that move M particle that I called gamma. And using this information and anticommutation relation, when I do my calculation, I get -1 as my phase factor. So I said that at the end, I did it. The situation was like I have two EM particles, then I change their places, right? So if I get a -1 after this operation, this means EM particle together behave like fermions. So this is the weird results that we have because in 3 dimension, if two different particles behave like bosons, and then if I use them together, they have to behave like bosons too, because each will have +1 when they change their places. So together they have to get +1 again. But in 2 dimension here, even though E and M particles behave as bosons normally, when I use EM particles together, they behave like fermions, which is impossible in 3 dimensions. So this is actually a really good example for the non-trivial braiding statistic, which was the second property of my topological order systems. So even though I have showed the 2 properties of topological order, there is a last thing that I want to show in my model, the ground state degeneracy. So here we need to remember some stuff that I have already told. I know that my star and placket operator take eigenvalue as 1 in the ground when I multiply the ground state, right? So actually this corresponds to only one state. Now let's remember the theorem that I have told before. The theorem says that if Hermitian operator commutes with themselves, then we can diagonalize them all simultaneously. So this means in my situation here, if I can find different operators which commute with my star and placket operators, and if those operators have different eigenvalue in the ground states, this means that I can say there are more than one state in my minimum energy level. So in the toric code, actually, there are only 2 more operators that sustain the properties that I have just said. So let's look at this figure here. There are only 2 loops, 2 independent loops. One of them is L1 and one of them is L2. And my operator that I just said consists of sigma z. And one of the operator acts on the L1 and the other one acts on the L2. So let's call them W1 and W2 here. So I know that sigma z can take eigenvalue plus or minus 1. In this situation, both W1 and W2 can take two different eigenvalues. So if I try to express my ground states, the eigenstates of these Hermitian operators, then I know that my star and placket operator only can have +1, but the other operators can have 2 different values. This results in the 4-fold ground state degeneracy in my model. So in summary, we know that topological order is important because it helps us to understand the phases that cannot be explained with the Landau theory. There are actually more general models in the topological order, but in the toric code, it's more clear to see the properties of topological order, which were energy gap and the non-trivial braiding statistics, which I have just shown. So thank you for listening. If you have any question, I will be happy to answer them.
Thank you for the brave talk.